Okay, so we're going to talk about improper integrals and the comparison test today. Quiz 4 is due next class, so don't leave without getting one. I'll pass them out towards the end of class. I handed out Project 4 on Friday. Just a little bit of a word of warning. Project 4 is one of the notoriously difficult projects in the course, so don't put it off till the last minute. Get some of the easier stuff done now. Problems 5 and 8 are particularly difficult. And next class, I'll just do it right now. At the beginning of next class, class 17, there's a little link that you can watch that will give you a hint on how to get through numbers 5 and 8. Okay, so you can watch that anytime you want. I'll post the link directly in Moodle too, so you can just click it. Yeah, be working on that project. Don't put it off. All right, what else? That's it. Project 4 and Quiz 4 are coming up. Okay, so today we're going to be able to determine whether an improper integral converges or diverges by comparing it to another integral whose behavior we know. So last class, we talked about the definition of convergence and divergence. So an improper integral was an integral that has some kind of infinite discontinuity. You're trying to find the area from 1 to infinity, or trying to find the area as you approach some kind of vertical asymptote. So converges, the definition of the integral converging means that there is a finite amount of area underneath the curve. Okay, so that any number, if you get any number as your answer, you say the integral converges. Diverges means that there's an infinite amount of area under the curve. Okay, so if you try to take the limit and you get infinity, then you would say that that integral diverges. So I have a cute little demonstration here that we have this big conclusion from last class, okay? So we were looking at integrals of 1 over x to the p. I'm using n here, but same thing. 1 over x to the p. The integral from 0 to 1, and then 1 to infinity. And we looked at the behavior for different values of p, or n in this case. So right now I'm using an n value. It's hard to see that from far away, huh? Let's see, I can't make it bigger. Sorry. Oh, how about this? That's better. Maybe 150. Okay, that's good. So now we can see the whole thing. So now you're using an n value of about 1/2. So when you're looking at the integral of 1 over x to the 1/2, the integral from 0 to 1 right now is finite, right? The area from 0 to 1 is this purple shaded area, and it's 2.22, right? But then the integral from 1 to infinity of 1 over x to the 1/2 is infinite. There's this pink shaded area. There's an infinite amount of area there. So this one we say diverges, and this one we say converges. And then as I increase n, you'll see that the area that's purple gets bigger. Okay, so I'm going to increase n a little bit. That purple area is getting bigger. The pink area is still infinite, still says diverges. And then at 1, I hit this magical spot, 0.951. At 1 over x, both of them diverge. There's infinite area from 0 to 1, and there's infinite area from 1 to infinity. And then after 1, we start to see that the area from 0 to 1 is now infinite. It's switched, right? So this is now the infinite area from 0 to 1, and the area from 1 to infinity is now finite, and it converges to a number. And then it stays like that forever. So that's our That's our big conclusion. I've got it written down in your notes here. Okay. If you're trying to integrate from any positive number to infinity, 1 over x to the p dx, it converges if p is bigger than 1, diverges if p is less than or equal to 1. If you're going from 0 to any positive number, 1 over x to the p dx converges when p is less than 1, diverges for p greater than or equal to 1. Sometimes it's hard to keep those straight. Just have them written down, right? Don't just guess at it. Have them written down in front of you. Put it on your note sheet for your test. All right, so last class, the only way that we could tell if an integral converged or diverged was to actually do out the whole integral and see if you get a number or if you get infinity. So today, we're going to be able to use what's called the comparison test to tell if an integral converges or diverges without having to do all the work of evaluating the integral. All right, so here's a picture. Totally ignore the formulas here. Pretend they're not there. So actually, I want the names, just not the formulas. So G is the pink graph, F is the blue graph. For what values of x is f of x smaller than g of x? No. Anything bigger than 1. This is the line x equals 1. Yeah, I think you were reading as the y-axis. Yeah, so from here over, right, the blue graph is below the pink graph, so that is all x's bigger than or equal to 1. Before 1, the blue graph is above the pink graph. Okay. So x is bigger than or equal to 1 is like a dividing line. F is smaller than g when you're to the right of 1. So if I know that the integral from some number a to infinity converges, that means that the area under G, the area under the pink graph here, is finite. Some finite amount of area under G, right? What can you conclude about how much area is under F? It has to also be finite because it's what? Smaller, yeah. If you're smaller than something finite, you have to also be finite, okay? So if I know that the integral of g of x converges, it must be that the integral from a to infinity of f of x dx also converges. Does that make sense? So if you can compare to something, if you know that your integral is smaller than something that converges, you can conclude convergence. All right, let's look at a slightly different scenario here. Let's say you know that the area under F is infinite. Okay, so you know that the area under F here, under the blue curve, that integral diverges, which means that there's an infinite amount of area there. How much area has to be under G now? Also infinite, right? Because it's bigger. There's more area under G than there is under F. If the area under F is infinite, the area under G has to be infinite too. Okay, so if the integral from a to infinity of f of x dx diverges, meaning there's infinite area under F, there has to be infinite area under G. So it follows that the integral from a to infinity of g of x dx also diverges. Okay. So these two statements together are called the comparison test. We're going to refer to it by name whenever we use it. The whole idea is that you have to come up with, you have some integral you're interested in. Does it converge? Does it diverge? You have to find another integral whose behavior you know, right? And either show that your integral is smaller than something that converges or bigger than something that diverges. What about being smaller than something that diverges? Doesn't tell you anything. Being smaller than something infinite doesn't tell you anything. You could still be infinite. You could be finite. Doesn't help. Okay? So you either have to be smaller than something finite or bigger than something infinite to draw a conclusion.
What if it was like something that's like a constant over x and smaller than x?
So you're looking at the integral. Which one are you trying to figure out?
Either one. It's like
well, we. Yeah.
Divergence.
Yeah.
Like the smallest divergence.
Well, I need a more specific question.
Okay.
Yeah. Okay, so we can show an integral converges if you can find a larger convergent integral. You have to show it's smaller than something that converges. Show an integral diverges if you can find a smaller divergent integral. So in practice, try to find a simpler function than the one in question, but with similar behavior, and then we look to compare it. All right, so I'm going to use the comparison test now, and I'm going to try to figure out what happens to the integral from any number to infinity of 1 over e to the ax, okay, for different values of a. All right, so I don't know the behavior of 1 over e to the ax. Does it converge or diverge? That's what I'm trying to figure out. So let's look at 1 over e to the ax. Any educated guesses? Does this thing converge or diverge? Assuming a is positive to start. Converge. Why do you think it might converge? That function with a constant in front of it.
You have negative 1 over a multiplied by
Okay, that might work. But if I was going to use the comparison test, if our conjecture is that this thing converges, I have to come up with another function that I know converges, right? And that this is smaller than. We only know one function, one family of functions with their convergence and divergence behavior, right? 1 over x to the p. Okay, so somebody give me a function that we know converges. 1 over x squared. Great. Let's compare these two. Which one is smaller? One over e to the ax. Yeah. You're going to think about which denominator wins, right, in terms of end behavior. So it's not just for small x's, but like if you put in a really big x, 1 over e to the ax is going to be much smaller than 1 over x squared. So in general, we've got that inequality. And I know that there is finite area under 1 over x squared. 1 over e to the ax is smaller than that. So there has to be finite area under 1 over e to the ax. So this is my comparison. This is the work that I do ahead of time, right? I know this one converges, this one's smaller, so it has to also converge. So then we have to really write this out using sentences and use the words the comparison test. So this is just a little bit of an introduction to proofs here. So we would say we know that the integral from a number to infinity of 1 over x squared dx converges. And then I'd say since 1 over e to the ax is less than or equal to 1 over x squared, then by the comparison test, the integral of 1 over e to the ax dx must also converge. You don't have to use that exact phrasing, but you do have to write a sentence, right? A sentence or two saying how you know what happens. All right, so we know that this thing converges when A is positive. All of our discussions there about 1 over e to the ax being smaller than 1 over x squared, that's only when A is positive. What if A is negative? It's going to diverge, yeah, and we can actually do a really easy comparison. If I have 1 over e to the ax, so this one was only for A positive. Okay. Think of A as like a -2, right? Yeah, Kevin. Nope, positive. Yeah. Any exponential, for any positive A, 1 over e to the ax will be smaller than 1 over x squared, even if it's like 0.2. Any exponential will beat a quadratic. Yeah. No, you're thinking of 1 over x to the p. Yeah, this is a new function. Yeah. Okay, so 1 over e to the ax. If a is -2, then I could rewrite this as, this is just e to the 2x, right? Which is an exponential growth function. So this thing is always going to be bigger than, I don't know, 1, right? And then if I want to take the integral from some number to infinity of 1, how much area is there under that curve? Infinite. Yeah. This is for A being negative. So if I was going to write a sentence out here, I would say, we know that the integral from a number to infinity of 1 dx diverges. Right? You can draw yourself a little picture if you need to. Here's my function. Right? The area under the curve from A to infinity, there's infinite area. It's an infinite rectangle. It's going to be infinite area. Okay. That diverges. So since 1 over e to the ax is always bigger than 1 by the comparison test, the integral from a number to infinity of 1 over e to the ax dx also diverges. Right? It's bigger than something that diverges, has to also diverge. All right, so my final conclusion here, this is for A less than or equal to 0. All right, so number 7 here are useful integrals for comparison. So I'm going to give you, in your activities and in your homework, random integrals, and you're going to have to compare to one of these three. You're going to use one of these three, usually one of these three, or some variation on them as your comparisons. So you have 1 over x to the p, whether you're going from a number to infinity or 0 to 1. And then you have 1 over e to the ax for a number to infinity. All right, so let's do a few examples together where I'm just giving you random integrals. So I want to determine convergence or divergence without having to do out all the work of getting the integral. Right? So the first thing I'm going to do here is I'm going to pull the 5 out of this integral. This is 5 times the integral from 1 to infinity of 1 over e to the x plus 1 dx. Okay. Now I'm just going to look at the integral and not the 5. If that integral is infinite, what's 5 times infinity? Also infinite. If that integral is finite, what's 5 times a finite number? Still a finite number. So that 5 is kind of irrelevant, right? So I'm just going to look at the integral 1 over e to the x plus 1. So my goal is I want to compare that function to something whose convergence or divergence I know, right? That is similar to this one. Okay. So what's a function whose convergence or divergence I know, but is similar to this one but simpler? 1 over e to the x. So I'm going to compare 1 over e to the x plus 1, compare it with an inequality to 1 over e to the x. Okay. Which way should I put the alligator? 1 over e to the x is bigger. Yep. The expression on the left here has a bigger denominator, which makes the whole fraction smaller, right? Okay, so we put a less than or equal to here. All right, what is the convergence or divergence behavior of 1 over e to the x? It converges based on what we just talked about. That's e to the 1 over e to the 1x. We look at our comparisons for our integrals for comparison. 1 over e to the ax converges as long as a is positive. Okay, so we know that one converges. Okay, so I have my integral is smaller than an integral that converges, which means my integral has to converge also. Okay, so we should write out a full sentence. So I'm going to say, we know the integral from 1 to infinity of 1 over e to the x dx converges. That's one of the 3 integrals I know something about, right? And we know that 1 over e to the x plus 1 is always smaller than or equal to 1 over e to the x. So by the comparison test, the integral of 1 over e to the x plus 1 dx must also converge, right? Because that integral is smaller than an integral that we know is finite. So I know that the area under 1 over e to the x plus 1 is finite without having to actually evaluate the integral. So it's just kind of a shortcut of knowing whether the area is finite or infinite without having to evaluate the integral. Oftentimes, once you know it's finite, then it's worthwhile actually doing the calculation. But today we're just determining whether it's finite or infinite. Any questions on this so far? All right, let's look at another one. So again, this 4 on top, I can pull right out of the integral. It's kind of irrelevant. This is 4 times the integral of 1 to infinity of x squared over x to the fourth plus 4x plus 1 dx. It's irrelevant because the remaining integral, if the remaining integral is infinite, 4 times something infinite is still infinite. If the remaining integral is finite, 4 times a finite number is still a finite number. Okay, so I don't need to take that 4 into consideration. Okay, so I have my integrand x squared over x to the fourth plus 4x plus 1. I need to compare it to something else whose behavior, something else that's much simpler than what I have here, but whose behavior we suspect might be the same. Yes, 1 over x to the p. What do you want to use as p? 2. Great. 1 over x squared. So explain to me why you're doing that. Why 1 over x squared?
Because the further you go out, like the closer you get to infinity, the last two numbers in the denominator become irrelevant.
Yeah.
And then it basically becomes 1 over x squared.
Yeah, we're kind of thinking about end behavior, right? Because this is going from 1 to infinity, this integral. So we're going really far out. We're talking big x's, right? So when x is really, really big, those last two terms in the denominator become less important. So if you drop them, you're left with x squared over x to the fourth, which just simplifies to 1 over x squared. Yeah. Well, L'Hopital's rule said take the derivative of the top and the derivative of the bottom, which was sort of a shortcut for thinking about end behavior. Yeah, yeah. So they're related. Yep. So now that I have a comparison set up, I need to put in an inequality sign, right? Which one should I put in, less than or greater than? Less than, yeah. I dropped these terms from the denominator, right? So when the 4x plus 1 exist, the denominator on the left is bigger than the denominator on the right, right? And when you have a bigger denominator, that makes a smaller valued fraction. So this is less than or equal to, always. This, I sometimes think, is the hardest part, determining, does the alligator go the direction you want it to go? If you need to, just pick an x value, like plug in 10 on both sides and see which one is bigger and which one is smaller. Or 100, any x value. Preferably a larger one, because sometimes right near the beginning of the integration interval, the inequality might not go the way you want it to, right? But we're going all the way out to infinity, so you just pick a big one, like 100 or something. All right, 1 over x squared, what does that do? Converge or diverge? Converge, okay. All right, so I have my integrand is smaller than something that converges, right? My integral is smaller than something finite, which means my integral has to also be finite. So I write it out with a sentence. Okay, so we know that the integral of 1 over x squared dx from 1 to infinity converges. And that my integrand, x squared over x to the fourth plus 4x plus 1, is always smaller than 1 over x squared. And so by the comparison test, the integral from 1 to infinity of x squared over x to the fourth plus 4x plus 1 dx also converges. All right, so our first two examples that we've done together have involved being smaller than something convergent. That's just the first part of the comparison test. Okay? If you can show that your integral is smaller than something that converges, that is this part. If your integral is smaller than something that converges, you have to also converge. So my third example is going to be this other one. You have, if the thing that you are comparing to diverges and your integral is bigger than it, then you also get divergence. All right. So let's look at this last one. Again, that 8 can just be pulled right out of the integral and it doesn't matter. 2 to infinity of 1 over the cube root of x squared minus 1 dx. All right, so I'm looking at my integrand, 1 over the cube root of x squared minus 1. I want to compare it to another function that's much simpler. It can only take 3 forms so far. There are only 3 kinds of functions I know the behavior of. 1 over x to the p, 1 over e to the ax. Okay, there's only 2 kinds of functions I know the behavior of. 1 over x to the p, and I can choose a p, and 1 over e to the ax, where I can choose an a. So I have to compare it to one of those 2. What do you want to choose? One over x? Any other thoughts? 1 over x to the 2/3. I like it. Yeah. Same kind of argument as over up here when we dropped the plus 4x plus 1, right? I'm going to drop this minus 1 because it doesn't make much of a difference when x is really, really big, right? Because I'm integrating from 2 to infinity. So I just drop that 1, and I get the cube root of x squared, which is the same thing as x to the 2/3. Okay. Which way do I put my inequality symbol? Greater than, yeah. This is bigger than that. And again, this is like the hardest part, I think. It takes a lot of thinking. But if you need to, you can always type into your calculator. Like, what if I put in a 10 here? Like, if I do 1 over the cube root, which is the math menu, cube root of 10 squared minus 1. Okay. 1 over the cube root of 10 squared minus 1. I get some small number, right? But then if I do 1 over 10 to the 2/3, I get 0.215, which is a little bit smaller, right? So the alligator eats the left-hand side, right? So just pick an x, plug it into both sides, see which way the inequality goes. All right, what is the behavior, convergence or divergence, of 1 over x to the 2/3? It diverges, right? That's 1 over x to the p, and p is smaller than 1, right? So this diverges. Okay, so my integral, my integrand, is bigger than something that diverges. It's bigger than something infinite. It has to also be infinite. So I write it all out with sentences. Say, we know that the integral from 2 to infinity of 1 over x to the 2/3 dx diverges. It's one of the 3 integrals that we can compare to. We know it diverges. And we also know that 1 over the cube root of x squared minus 1 is always bigger than or equal to 1 over x to the 2/3. So by the comparison test, the integral from 2 to infinity of 1 over the cube root of x squared minus 1 dx must also diverge. So you got to be a little bit careful. All of my examples led to valid conclusions. It's really easy to go down the path of comparing to, if you compare your integrand to something infinite, if your integrand is smaller than something infinite, that tells you nothing. Okay. So make sure that when you're comparing, you either have to be smaller than something finite or bigger than something infinite to get a conclusion. All right, so that's it for the demo. And now you've got several to try on your own.